2, 1.
Hello, this is Oppo, a packet to investigate GPU deep packet processing acceleration. Our team is composed of team lead Devin. Would you like to introduce yourself?
Yeah, how's it going? I'm Devin. I've been more or less coordinating with the project. Anya and Daniel are taking development and design leads, and Connor has been our liaison with our client Cisco. Well, not technically Cisco, but namely Doctors Jay Ivor and Sabarthi Paul, who've been working with us on this.
Yeah, Devin's emphasizing that this is not a product we're building. This is a research question that doesn't have funding allocated. Connor and Anya and Daniel. Okay, to frame the question of to frame our research question here, it's good to understand the state of packet processing in the world as it is. Here's a dive from Cisco's Quantum Flow Processor, which is a highly specialized bit of hardware for doing very similar work to what we're doing very fast. That is, at least part of that is extracting, say, OSI layer 2 through 4 from packets, typically for the purposes of packet forwarding, and up to layer 3, thereabouts, IP, and below. This is typically done in hardware. If you open up any router going back to certainly the 2000s, maybe even the 90s, you can see CPLDs, FPGAs, some ASICs that are built over a very long design cycle for packet forwarding and firewalling. But without more generalized hardware, as we can see on the next slide, like a CPU, deep packet processing that supports all of the different protocols as one goes up the network stack is impractical on specialized hardware. That needs to be done in software, which is written for general purpose computing devices. Modern Cisco products, Cisco routers and flow processors take the ASR 1001X, very popular one, has a Xeon in it for this purpose. So this is the state of the art, and there's only so far that specialized hardware, even the GUI middle area like FPGAs, can go.
Okay, so like the motivation for this project is mostly to see what we can do on a GPU, which has a lot of like accessibility parallelization as opposed to a CPU. And so like as I said before, like other kind of methods of doing like deep packet extraction is often going to be done on very like costly or like very specialized hardware. And so because GPUs are so widely available and so popular now, especially since like they've been like used a lot in like artificial intelligence, and we were looking to use something popular like GPUs to try to provide some like development on deep packet parallelization. So our approach to this project is to look at 3 to 4 different like methods of analyzing and parallelizing for the performance. So the first would be to do a traditional batch processing and exploit the architecture of GPU to do everything in parallel. And with this kind of method, we'd probably want to start with fixed size packets. And then after that, at the same time, we'd also want to explore using like a dynamic data management scheduler dynamic data management or scheduler. So like if we are using not fixed size packets, we don't want to be at the will of like the longest size packet, so that hopefully, so we can kind of keep things going and not just be stuck by the longest packet. And then we'd also wanted to explore layer by layer batching with multiple scheduling rounds per packet. And so there's like multiple layers in packet, and so like from like the data we gather in each layer, we could probably rebatch our packets to put more similarly typed packets together, which could also hopefully have some kind of speed up. And then also just minimizing I/O. And so this is all the kind of things we'd be looking at in our different approaches.
I think it's worth expanding for the general audience here a little bit of how a GPU works and why we think we can get a packet processing speed up from it, particularly with deep packet processing. The general architecture of a CPU dedicates a great deal of its silicon to control and caching compared with the GPU, which has, typically a CPU will have anywhere from 1 to 20. Some of them I've seen 96 cores, but say 20, comfortable average. GPUs get into the hundreds and thousands, but these cores are much simpler and are, and again, have reduced cache and are good at processing a smaller number of simple instructions on large chunks of similar data. The great challenge of our research question here is that network packets in their layered structure are not conducive to parallelized processing within a single packet, as each layer must necessarily be processed sequentially. But we hope that by buffering these, by batching these packets, that is, for example, putting 100 packets, each one after the another, each in separate GPU cores for processing, we might be able to get some throughput increases that offset the additional power consumption of the GPUs and the additional latency of GPUs. Regarding ambitious I/O minimization, one of the new offerings of our project is to put all of this onto the GPU so that raw packet data goes in and all the information we're looking for, that's every feature extracted from the packet, is exposed to the API on the outside. So rather than switching batches of data back and forth quickly between the CPU for different stages of processing, incurring massive I/O latency, moving between devices, doing it all in one place should minimize that.
Okay, so like I said, our client is technically not Cisco. We're working with Cisco on their research initiative. There are some questions of, I'm sorry, I'm saying that wrong. Where you decided to use the CUDA API, which is specifically for NVIDIA hardware. This is partially something that's been specified by our clients, and partially due to availability of resources and it being open source, which is why we see our friend Linus Torvalds down there being
Richard Stallman,
being one of our stakeholders for the open source community. One of our big goals of this project is to make a simple API that kind of generalizes this packet parallelization.
Yeah, that is to say, we're open sourcing our project, thus the open source community being a potential stakeholder. We are in something of a conflict because NVIDIA's CUDA API is very much a closed source project. So it's unlikely that Free Software Foundation diehards like Richard Stallman would be interested in using it. But nonetheless, as an open source project, it deserves mention as such.
Okay, so these are engineering requirements that we came up with after talking with our client. Like it was mentioned before, we basically have to use CUDA, and they gave us a pretty wide leash on what we can do within our realm of packet processing. So for example, some of the requirements we came up with is we want to parse different types of headers, and where we say the risk is low is where they're fairly simple headers and they have a simple structure in how they work. First, some of our reach goals would be like decrypting a TLS packet, which is just a bigger packet, lots more stuff going on, and so that's why we say the risk is high. And we also put other things on here, like ideally we'd keep the latency pretty low, but getting that is also a reach goal, so we'll go with that. And yeah, we also put different APIs and programming languages. Currently, CUDA supports C, C++, and Python. And so we put those at medium to make sure we could figure out which ones we wanted. Okay, and so this is our concept fan. We came up with it when we were first starting to think about parallel processing, kind of divided our thoughts into two processes. There's the hardware and the software. And so on like the software side, we were thinking more of the like GPUs, CPUs, and the differences between those and like the different architectures and how they work pretty much. And on the software side, we were thinking, again, because we have an option to use different programming languages, C++ or Python, and the different advantages and disadvantages of those programming languages. And then we decided to also think about Linux because it's very open source. You can do a lot of stuff versus like using Windows where GPUs are widely supported for graphics use and stuff like that. But Linux just makes it very easy for us to access the stuff we want to do. And then here is a design decision matrix where we decided between C++ or Python because those were our two options. And so we wanted from the get-go to know which direction we want to go in. And so we, based on our group here, we came up with these criteria and assigned a weight to them based on our personal experience and feelings about the two different things. And we computed them and decided to go with C++ because got an overall better score and feel that it would be better for our project.
Clarification, kernel code here refers to a CUDA construct. A CUDA kernel is a set of code that is run on the NVIDIA GPU. That is not the same as an operating system kernel at all.
And so as far as goals and objectives go, our ultimate goal is to have a program for deep processing of packets on the CUDA API with a simple user interface to our project. Along the way, we're interested in what assumptions we have to make, what complications may arise in fully implementing on the GPU, because a part of the project is ultimately trying to cut out CPU and GPU swap of just giving the data to the graphics processor and having it do the parallelization. And ultimately, yeah, assessing the viability of replacing or having an alternative being GPU. We definitely are going to need to support the basic packet types, like Dan was mentioning, up to layer 3 and 4 is not trivial, but more or less straightforward to extract data. Once you get into TCP and higher protocols, you can get more complicated, which brings us to the last goal of bells and whistles. Once we get to those higher layers, things like TLS stream reassembly, TLS description or decryption, so that we can use the program to see what's in the packets and then also do something with that information. So as of today with our demo, we've been working on development to the extent that we need to understand the CUDA API and how graphics processors work, as well as basic feature extraction. Over the next few months, we're going to be implementing our basic batching, getting that working, and then experimenting with more complicated strategies to speed up the throughput or increase the throughput. Software validation is more or less checking to see if we can complicate it faster or more complicated than just batching of packets. And evaluation measurement is analyzing the differences between those methods. And as a research initiative, there will be a heavy emphasis on documentation on our findings.
Any questions?
Yes.
Is there like a fast explanation for what you mean by layers when you're talking about packets? Layers.
So by nature of how network packets work, it's called encapsulation. So on an application, if you wanted to send something, you take your data and you wrap it in metadata, which is called like a header, and that you pass it down the protocol stack to a different piece of hardware. So from the application, you want to communicate, for example, something over TCP, and then the hardware below it deals with IP, or actually probably software still deals with IP. And then once you get down to Ethernet, it's just data on the packet that's referring to which port on which device it's going to. And so that's more or less the feature extraction. So it's on this particular packet, what ports is it going between, what IPs is it going between, all that kind of metadata. And there's different layers depending on what piece of the data you're working with, or what layer.
And inside that IP packet, there might be HTTP if someone's browsing the web. It has to go across your local network, and has to go across the wide internet, it has to get picked up by your computer, and it decodes all of this to get the web page, the cat pictures inside. we're looking at not just the shallow processing, which we're defining up to IP thereabout, but also all the way down to HTTP, which can't really be done in hardware right now. Too variable.
So I was just kind of curious if this was like the project was an original idea pitched by Cisco, or there's like some previous research that this is sort of based on.
Yeah, there's a very large body of work, and the literature is a little bit interesting because there in the last, I think, 4 years, there have been a set of sort of mutually progressing papers that were arguing that yes, GPUs, more parallelization, more better, we can do pretty much anything faster. That was published by NVIDIA. Intel published a paper saying actually GPU acceleration is faster, but what's really going on here with packet processing is you're using parallelization techniques that we can also do on a CPU. It's just that the GPU API, which requires high parallelization, encouraged a certain type of programming that hid data access latency. So Intel did something that performed just as well on the same experiments on CPUs. But this, we suspect that with specifically in deep packet processing, with a little bit more algorithmic rather than systems programming approach, we can still get some gains. And even if we can't, we consider it a success for the scope of our project to determine that that is impossible. We're answering the question rather than producing a product. We're not trying to outcompete Cisco or Intel. We're just trying to follow the GPU lead to its end, whatever that may be.
Is this literature available to someone that doesn't want to pay for it?
It's a good question. We got it from our client. I will see if I can send you links after.
I think they're public links.
At least a lot of them are, at least. Yeah. I wonder about the APU one though. Okay.
Yeah. It's available.
Okay, great. They're all available. Any other questions? All right, thank you. Sorry, thank you for the question.